Hi, everyone. Today we're talking about inelastic collisions and ballistics. The perfectly inelastic collision is actually used in forensics sometimes to gather more information about a specific gun type or things like that. So we're actually going to use actual forensic method to uh, solve one of our physics problems. But first, let's talk first how to find and solve a perfectly inelastic collision. So our first slide says that a 2,000 kilogram car stopped at a traffic light is rear-ended by a 1,000 kilogram car and it becomes entangled. So that makes it perfectly inelastic, right? They stick together. If that smaller car was moving at 30 meters per second at the moment of collision, what is the speed of the entangled masses immediately after the collision? So let's get our givens here. Our car 1 sitting still is 2,000 kilograms, so its V1 is 0 meters per second. Mass 2 is 1,000 kilograms, and its initial speed is 30 meters per second. Now we want to know the final. What is the velocity of the entangled masses after the collision? So to look at a perfectly inelastic collision, we have to remember, you've got the summation of momentum initially equals the final momentum as well. But we've got m1 v1 plus m2 v2. That's going to equal the summation of masses times one final velocity because they're being combined, right? They're going to stick together somehow, and they're going to move with one common velocity. So if we want VF, let's divide the sum of masses over. So you've got M1 V1 plus M2 V2 all divided by the sum of masses. And that will give you V final. And luckily we have all of that, so we can plug this in. You've got 2,000 times 0, so that goes away. Then you've got 1,000 times 30 divided by the sum of masses. 2,000 plus 1,000 will give you 3,000. Put that in your calculator. You should get 10. Yeah, 10 meters per second is the final velocity of this entangled mass. Now, this crash is actually pretty violent. If you look at the actual numbers, 30 meters per second is about 67 miles per hour, creaming this stopped car at a traffic light. And it's actually going, I think this is something like 22 miles per hour. So it actually hits this car really hard, and the entangled mass is actually moving really fast. So these numbers are actually really high for a car crash. But anyway, this is the method that we're going to use for a perfectly inelastic collision right here. Take the two momentums separately to start, but they will have a final momentum together because they are combined. All right, next, we have the forensic analysis with physics. Okay, so to analyze a firearm suspected of involvement in a crime, a bullet is fired into a large block of wood suspended by a light wire. The bullet embeds in a perfectly inelastic collision and swings to a maximum height h. Now derive an equation for the speed of the bullet at the moment of impact. So we want to know how fast this bullet can travel. That can help with the forensic analysis. Here is an actual demonstration of it. Okay, so here is from our textbook over here. Okay, you've got the bullet traveling into the block, and then you can see it's got these light wires to it. And then it's going to swing up to some height h over here, and that height h is going to be important, right? If it's going faster, it goes higher. If it's going slower, then it won't go quite as high. And then this seems to be an actual demonstration where it looks like he's firing something, and it travels up here. That doesn't really look like a gun, but he's firing something along this path. So if we want to analyze this, okay, we know it is a perfectly inelastic collision. Okay, so you're going to have, let's call mass 1 bullet and mass 2. Mass 2 will be the block. And that comma is misleading. There we go. So what we have here is a perfectly inelastic collision, right? We have M1 V1 plus M2 V2 equals the sum of masses M1 plus M2 times this V final. And what we want to know is the velocity of the bullet before this collision. So we do know that the block is sitting still, right? Because the velocity is 0, so we can get rid of that. So if we end with M1 V1 equals M1 plus M2 all times V final. If we want V1, let's just divide. Divide all that by, divide by M1, and we'll get our answer, right? However, V final is going to be tricky. At what point do you measure the velocity? Okay, it seems to be that when they're doing this experiment, they're really measuring h, not velocity. So if we're going to measure the velocity of the block bullet combo in a lab, at what point do you actually measure that? Do you measure it the second after it's traveled? Because that block may travel quite a ways in 1 second, right? Do you go at half a second, a millisecond, a nanosecond, a microsecond? What are we talking here? So we don't want to rely on V final. We don't really have a super reliable way of measuring that, and some labs may be able to measure the velocity in different ways than others. Some are more precise than others. But one thing that they do have in common seems to be that they can measure this height in the lab. So let's give this a shot. Let's see what we can do about that. So if you use a COE, a conservation of energy problem, we could actually get velocity in terms of height. So if we say the kinetic energy after the collision is equal to the gravitational potential energy at the top of that swing, right? So this is this is when the masses are combined, right? The bullet has been fired, and this is the moment those two masses have become one. They will move with one common velocity, and that is going to be the kinetic energy we're talking about here. All of that kinetic energy of this combined mass will swing up to a height, and it will stop. Because we could actually say, right, that there's a K final here, and we're going to say that it's 0. We're looking at when it comes to rest. So if we want to do that, we will say that this is 1/2 M1 plus M2 times V final squared, right? This is kinetic energy, not momentum. Then you've got the masses M1 plus M2 times GH, because our equation for UG is MGH, right? Hopefully you remember that. Now, we do have M1, M2 on both sides. We can get rid of that, divide that out. If we want to solve for VF, because that's what we're trying to substitute in, right? We're trying to substitute for VF, we have to solve for it. So if we have VF squared, that equals 2GH. That means that VF is the square root of 2GH. So we can actually substitute that up here to say that the velocity of the bullet is the summation of masses times the square root of 2GH, all divided by the mass of the bullet. So here, this is actually going to become common in our conservation momentum problems. As these problems get more and more complex, we're actually going to use other tools to accompany our conservation of momentum, such as here using conservation of energy to help us out. So this is our equation for the velocity of the bullet before the collision, right? Because this is our before, this is our after. So this is our equation that we're going to use. Now for the next one, we're actually just going to plug in some numbers. Okay, the results of the ballistic pendulum experiment are that it swings up a height of 5 centimeters. Now remember, that's not the arc, that is the change in height. specifically. So it's a change in height of 5 centimeters. Mass of the bullet is 5 grams. Mass of the block is 1 kilogram. Show work to check a colleague's analysis. Your colleague says that the initial speed of the bullet is 199 meters per second, and that there is a loss of mechanical energy during the collision of 98.5 joules. So let's see how we're going to do this. First, let's bring that equation down. We had the velocity of the bullet is, I said I would give it a 1 there, m1 plus m2 times the square root of 2gh, all divided by the mass of the bullet, right? Now we have some numbers to go along with that. M1 is 0.005 kilograms, because that is 5 grams, right? Mass 2 is 1 kilogram. G is itself, it's G. H is 0.05 meters to show that it is 5 centimeters. That's all we need. Let's get to it. Let's see what the initial speed of this bullet would be. We've got velocity is the masses added together, so 1.005 kilograms times the square root of 2 times 9.81 times 0.05, because it travels, remember that's a height of 5 centimeters, divided by the mass of the bullet, 0.005. Put that in your calculator and you get something along the lines of 199 meters per second. That's right. It is true. Your colleague is correct. You get 199 meters per second. So that we solved from our previous problem, right? We had the equation. We just needed the results of the experiment. We can plug that in. Now here, we have a loss of mechanical energy during the collision. Now, this is something that we talked a little bit about in the last video, but remember, perfectly inelastic collisions, kinetic energy is not conserved, right? Only inelastic collisions is kinetic energy conserved. That doesn't mean that energy is not conserved all around. However, we do know that there is going to be a loss of energy due to friction and heat as that bullet embeds itself in the block and it starts moving, right? That's just intuitive that you're going to lose energy on that collision. So we want to know how much energy loss there was. And your colleague says that it's 98.5 joules. We can actually solve that. So up here on our COE, remember this is the kinetic energy when they are combined, 1 plus 2. So this is after the collision. And then obviously as it swings up, this guy is way after the collision, right? So here we're not looking at the before after collision energy change, because after the collision, we're saying that there is energy is conserved, right? It's going to swing up. There's no loss in energy as it swings. We're saying that air friction is negligible. But your colleague says that there is a loss of mechanical energy. First, let's talk about what is mechanical energy. So the mechanical energy of an object or of a system is the summation of all kinetic energies plus the summation of all potential energies. The only potential energies we've talked about so far in this class are gravity and springs. But if you take all the summation of those kinetics and potentials, that is the mechanical energy either of the object or of the system. Now, we have a mechanical energy loss. This says that the change in energy equals negative 98.5 joules, right? That's what your colleague claims. To find the change in energy, okay, delta E would just be the final minus the initial, okay? So let's see, what is the final energy? Well, the final energy is going to be actually the tougher one to find, right? Energy final. If we want to know the energy after the collision, we can either look at the kinetic energy after the collision, or we can look at the gravitational potential energy after the collision, because we already showed that those two must be equal to each other. We did that already. Now, you can choose either or. I'll actually solve both for you real quick just to show that they are going to be equal. The kinetic final would be 1/2. Remember, this is after the collision, so you've got combination of masses times V final squared, and we just solved for V final, it being, what did we have? Oh, we actually didn't solve for that. It's square root 2GH, right? So let's get that real quick. VF equals square root of 2GH. This is square root of 2, 9.81, 0.05. That gives you 0.99 meters per second. Basically 1 meter per second. So that's a big change in velocity, right? You're going from almost 200 meters per second to basically 1 meter per second. Massive change in velocity, but remember, conservation of velocity is not a thing. So we don't need to hang up too long on the change in velocity. So we can do that. We'll plug that in here. You can also find UG, which would be M1 plus M2 times GH. We have all of that. So let's plug these in. Let's get 1/2, 1.005 kilograms times 0.99 meters per second, and that's all going to be squared. Then here you have 1.005 kilograms times 9.81 times 0.05 meters. If you do that math, these are really close. Okay. Here you get 0.4925. What is it? Oh, that's joules. Okay. And then here we get 0.493 joules. That's really going to come out to 0.49295, which is around, you would round that. Okay. So really close, right? So we get basically 0.5. We'll call that 0.5. Okay. Now and that is the energy final, right? We said that you can do one or the other. We did one or the other. They are both basically 0.5. So let's say that the energy final is 0.5 joules. Okay, so that's our delta. If we want delta E, change in energy, we start with 0.5 joules. Now we need to subtract our initial energy. The initial energy is just the bullet, right? The block is sitting still. So we need the kinetic energy initially of the bullet, which would be 1/2 times the mass of the bullet, which is 5 grams, or 0.005 kilograms, times the velocity, which we found was 199 meters per second. We got to square that. That will come out to about 99 joules. So if you take 0.05 minus 99 joules, you get negative 98.5 joules, which is just like as your colleague said. Right? Now that is a ridiculous energy loss, right? You have an energy loss of almost, I think it's over 99%. Let's see, 98.5 divided by 99. Yeah, you are at 99.49%. 99.49% energy loss. Crazy high on that one. And that's how much energy you're losing when a bullet gets lodged into a block. But since we can calculate all that, we can actually account for it, and we can work backwards to find out the velocity of the bullet. That's all we have for this video. In our next video, we're actually going to look at how we can use conservation of energy and conservation of momentum in the same problem interchangeably to help us find the correct answer.